All right, today here we got 10.1. We're going to talk about sequences, series, and then sigma notation. Essentially, what a sequence is going to be is going to be a order list of numbers. Usually, there's going to be some type of pattern to them more times than not. Each of the individual things in the sequence, we're going to call those the terms. And then you're going to have two different categories of sequences that we're going to look at today. We're going to have finite and infinite sequences. So a finite sequence is a sequence that has a finite number of terms. So it doesn't just keep going on forever. We say that it eventually ends. And then an infinite sequence is a sequence that has an infinite number of terms. So that is that right there. Each term of a sequence is a function of its position. Therefore, an infinite sequence is a function whose domain is the set of all natural numbers, and can be written as usually we'll write f of 1. So you're inputting 1, that's going to be written as your first term right there. And then a, and then this is called subscript right here, a subscript n right there is going to denote the nth term. And if the domain of a sequence is only the first n natural numbers, then the sequence is finite. Okay, so a little wordy there. Anyways, let's dive on into this here. You're going to have some examples here. Find the next four terms of the sequence here. So what I'm going to try and look for is see if there's some type of pattern. Now, on the 10.2 and the 10.3 day, you'll look at very specific types of patterns, but these could literally be anything. Like here on these, it looks like you're adding 5 each time here. So the next one here we'll get by adding 5 as well, so that'd be 22. You can add another 5, that gets you 27. Add another 5, 32, and then 37. Those would be your next four terms right there. Now, next one right here, this one's a little bit different here. If you look, there is some type of pattern with addition, but it's just a little bit different here. On this one here, it looks like you're adding 3. Next one over, it looks like you're adding, what is that, adding 5. And the next one right there, that is like adding 7 right there. So it looks like what you're doing each time is you're adding, I guess, 2 to what you're adding to each time right there. So it's basically like these like a second level of adding here is you're adding 2 to what you're adding to previously, and you call it a second difference. You kind of talk a little bit about that in calculus. That's essentially what's going on here. So the next one here, I believe, would be adding 9. So if you add 9 onto that 17 there, you get 26. If you add 11 for the next one, that'd get you the 37. The next one would be adding 13, so I think that'd get you out to 50, and then the last one would be adding 15, which would get you out to 65 right there. There's also kind of a way, like if you want to write this here as an equation, if you notice here, each of these numbers here are 1 bigger than a perfect square. So if you think about this here, if you write it out as like n squared plus 1, you can go and plug in for n and then find different numbers. So if you input 1 right here, 1 squared plus 1, that would get you 2 overall. And that should work for each one of these here. Like for example, if you plug in 6 squared plus 1, that would get you the 37 right there. So it's kind of another way you can think about it there. You can get an equation, or you can kind of use your pattern there. So okay, this next one here, find the first 4 terms of the sequence given by this equation right here. So this is a sub n. This is the nth term. So it's kind of a generic thing here for right now. And then you take 2 times whatever your n value is, and then -1, and then raised to n right there. So how we're going to find the first 4 terms here is you stick in a 1, you replace a 1 with the n. And what that would look like actually in the equation plugged in is this right here. And then you would just go and simplify that. A negative raised to an odd number there will stay negative, so basically that's -1 times 2, come out to -2. And you can just go through and do the first 4 terms there. On this one here, if you do 2, it'd be 2 times 2 and then -1 squared. If you square a -1, that should come out to +1, and then +1 times the 2 times the 2 should come out to +4. And then you can keep getting the rest. -1 to the third power will stay negative, so that I think becomes -6 there eventually. And then finally to the fourth power. Oops. Oh, hang on, I wrote that wrong. -1, and then to the fourth. That would make that positive, and then positive times the 8 would get you +8. So there's your first 4 terms right there in that sequence. So sometimes they give you a pattern, sometimes they give you an equation. You can do both right there. That formula above is going to be called the explicit formula. You're going to have 2 types of formulas that we use, an explicit formula and a recursive formula. The explicit formula is the most useful, in my opinion, because it helps you find the nth term in terms of n. So basically, you can plug in whatever n value you want, and you can find the nth term. So if I wanted to find the 100th term, for example, you could plug in 100 and actually go figure out what the 100th term is. The next type of category for sequences is what's called a recursive sequence here. So sequences can also be defined recursively. These sequences give one or more of the first few terms, and then they define the terms that follow using the previous terms here. And that's kind of the big thing here with this. You use the previous terms to find the next terms here. The formula for deriving the nth term of a sequence is called a recursive formula. Okay, or sometimes you might see a recursive relation, but recursive formula is good there. Here's what they kind of look like here. Typically, they're going to start you with the first term right here. Now, I'd even write this down if I were you. Okay, a sub n represents the nth term still. And then here's what's kind of weird. So they're not going to actually give you an n typically to plug in. Sometimes they will. I guess this one does. But this right here is going to be the previous term. And the reason it's the previous term instead of the nth term here is you do n minus 1. So it's the 1 right before that right there. So with these recursive formulas, you have to have the previous term to get the next term. So you can't really skip. You can't start at the first term and then get the 100th term. You'd have to go one at a time to go get the 100th term. So they are not as useful because you can't go, I guess, as quick. You can't find quickly what term you want. You have to find one after the other. Okay, so that's kind of the big things there. So let's see here. This says find the 5th term of the recursively defined sequence right there. So we already know the first term. A sub 1 is going to be 1. Okay. And then A sub 2, here's how you go and find this here. So I'm going to plug in, I'm going to say that left side here. Here, I'll write it horizontal. A sub 2, like that right there. And then you can put A sub 2 minus 1, kind of like that. And then I guess plus, and then 2 times your n value, so 2 times 2, and then minus 1 like that. Now here's the deal. This part right here, go ahead and underline that. That is a sub 1, and we already know a sub 1 is actually 1. So this is going to come out to 1, and then plus 2 times 2, and then minus 1, and then we'll simplify that down there after that. 2 times 2 is 4, 1 plus 4 is 5, and then 5 minus 1 should come down to, I guess, 4. Okay, and then that should, I guess, be that. Sorry, I was looking at my notes here, says something different, but okay. So now let's do a sub 3, and I'm going to skip 1 or 2 steps here. So we'll do a sub 3 equals, let's see, oh, whoops. A sub 3 will do the previous term. I'm going to go ahead and skip and just plug in 4 right away here. So I'm going to plug into 4, the previous term. That's what we did right there. We plugged in the 1 on the last one. Now we're going to plug in 4. And then our n value is going to be 2 times 3. And then we'll do minus 1 like that right there. So we'll simplify that. That is going to be 4 and then plus 6. And then minus 1. That's going to actually come out to 9 right there. Let me scoot these over here a little bit. That's how you're going to do that. Now we'll rinse and repeat here. We'll do a sub 4. what that is. So previous term again, the n minus 1 part right there, that's your previous term. So that'll be, what was that, 9, I guess. And then 2 times, and then we're inputting 4. So that's going to be 2 times 4, that's 8. So you got, what, 17 minus 1, that'll be 16. All right, and then finally, the fifth term. So take your previous term, that's what the a sub n minus 1 right there is, the previous term, so 16. And then 2 times your n value, which is going to be 5, and minus 1 right here. So it'll be 16 plus 10, and then minus 1, that'll come out to 25. I think it's kind of a coincidence, but these all happen to come out to perfect square numbers right there. So you could probably actually come up with an explicit formula, a more useful formula to go find your next term there. So that is how you do those. Okay. All right, let's look here. I think we do deal with another recursive formula in a second, but we'll get to that in just a moment here. Over the course of this class, you've evaluated end behavior of the graphs of the functions. And you learned that domains of some functions approach infinity. And then the ranges approach a unique value, and sometimes we'll call them a limit. I think, I've said in previous classes where they level off at. Typically, those are like those, maybe the reciprocal graphs that you've done, or maybe even the exponential graphs. Like maybe they level off at like 2 or 1 or something like that. So whenever it levels off, essentially you're going to say it converges. That's the vocab for that. And if it doesn't level off to some consistent number, then you're going to say it diverges. The big thing with converging is make sure it levels off to a unique number. Okay, so we're going to see a few examples that converge and diverge here down below. So first of all, this sequence right here, it's given, they give us the explicit formula right here, so we can input in and find any term we want. So what I would actually recommend here is actually figuring out a few of these, and then seeing if you can tell if it's leveling off at a number or if it's like gonna like infinitely increase or decrease. So here's kind of what I mean by that here. We'll do 3 and then times 1 and then plus 12 right there. I think that comes out to what is that? Negative 3 plus 12. That come out to 9. Okay, we can do the next one here, negative 3 and then times 2 and then plus 12 right there. I think that comes out to 6. Next one here, that would be 3. Whoops. Plug in a 4 right there. That'll be negative 12. Negative 12 plus 12 will be 0. So you can kind of see each time here, it looks like they're subtracting 3. And that is tied to the slope of the equation here. So I'm going to kind of skip here. I can kind of tell the pattern here. This one's going to be negative 3. A sub 6 would be negative 6. So it's always decreasing by 3. Since that's not ever going to level off at a number, it's not going to just like get closer and closer to like 0 or closer and closer to like negative 10. Like it's always going to decrease by 3. We're going to say since that's happening, this is a divergent series. Or I said series, I meant sequence there. Series we'll talk about here in a second. So that's that there. That one's pretty straightforward there. Just does it level off or not? The next one, they don't give us the explicit formula. They give us the recursive formula. And I know that because I see this n minus 1 thing right here. A sub n minus 1. Right there. Don't forget that's the previous term. So we'll need the previous term to get the next term here. So usually they got to start you out somewhere. So they'll start you with the first term here. So a sub 1 is 36. A sub 2, so here's what you do here. You apparently do 1/2, negative 1/2, and then times your previous term. And then this part right here, that's just saying like you can't plug in any values for A. You can't do anything less than or equal to 2. So you got to start somewhere. You can't start with the n value being below that. So anyways, so we're going to take the previous term. The previous term was 36. Negative half of 36 would be negative 18. And we can keep going here. A sub 3, negative half of negative 18 right there. That should come out to positive 9. A sub 4, negative half of 9 right there. So half of 9, I guess that'd be negative 4.5, or 9 halves if you want. 4.5 is probably good. You can keep doing this here. Basically, you're doing half of your number every single time. So you can keep doing this half of the number. It gets kind of smaller and smaller every time. The gap between these is getting smaller every time. So this gap is going to consistently start to decrease here, which means something specific. This next one here would be 2.25. So you can keep doing this forever. Eventually, when you get to like some giant number, eventually it's going to come out to where it levels off at 0. And since it's leveling off here on this one's going to be one of your convergent sequences. So this one is convergent. It levels off at 0. Now some of y'all might be saying, well, isn't it switching from negative to positive each time? But it doesn't really matter if you're switching between negative and positive, because eventually you're going to get close to 0. Like they're all going to round to 0 eventually. So that is why that one's going to be convergent. Now this next one right here, this one's a little bit weird, just because of the way it looks right here. What I would use on this one here is use your calculator. What I want you to do is type into y equals in your calculator, and then I want you to look at the table. And I'll write out the math for maybe like one of them here, but I'm going to list out quite a few of the values here on this, and then we're going to talk about what that comes out to right there. So if you plug in 1 right there, you can write it out if you want. I'm not going to do this for every one here, but you'd raise that to 1, you times it by 1, and then you do 4 times 1 plus 1 right there. I guess that'd eventually come out to negative 1 in the numerator, and then 5 in the denominator right there. So we're going to say that that is going to be negative 0.2. And I'm actually going to use a lot of decimals here for these. So that's your A1 value. I'm actually going to write A2 over here to the side. Just kind of watch how I do this here. I already kind of know what's going to happen. So I'm going to write out the values. So I'm going to get the rest of these by looking at the table in the calculator. So just type this thing in. Instead of n's, you can change those all to x's right there. And then look at your table. So here, let me copy these down here. A sub 3, negative 2.31. A sub 4.235. A sub 5, negative 0.238. And you can keep going through this here. I'll probably just do one more set of these here. And then A sub 8. Yeah, 242. Okay. So what's happening is some of them are getting kind of close to negative 2.4. I think it actually is going to come out to where it's eventually going to come down to negative 1/4 or 0.25. And then our other one here is going to eventually come out to positive 1/4. And since it's not where like both of them level off to 0 eventually, they're one's going to 1/4, one's going to negative 1/4. Since it's not a unique number, we're going to say technically this one, even though they're kind of going to their own different numbers, they're not going to one common number. So we will go ahead and say that this is divergent. And that is kind of a special case, honestly. More than likely, you'll see like these two here on tests and quizzes there. But that's using a table to kind of go and quickly figure out that it's going to be convergent. So let's try out this next thing here. So series coming up. Series is going to be the sum of all the terms in a sequence. Okay, and you'll have two different types of series. You can have a finite series and an infinite series. A finite series is just the sum of a finite number of terms in your sequence. And an infinite series is the sum of an infinite sequence, which I think we do here a little bit later. We got some notation for it, but we're going to add an infinite number of things and actually figure out what the sum is. Okay, What else we got here? Oh, nth partial sum, which is what we're about to do here, the sum of the first in terms of a sequence here. So like down here below, they're going to say find the fourth partial sum of this thing. So what does that mean? That means find the sum of the first 4 terms. Okay. Now there's going to be some formulas that you're going to learn for sums here of very specific type of sequences, but we don't really know if this sequence is going to follow that rule. So what we're going to have to do is by hand figure out what A1, A2, A3, and A4 are going to be. Since they gave us n and not the n minus 1, we can go find these in any order we want. Actually, just to prove a point, I'm going to find A4 first because you don't need the previous term to find that. You can just stick 4 right in. And then I guess add the 3 there at the end and figure out your number there. Negative 2 to the 4th should be positive 16. Positive 16 plus 3 right there should come out to 19. So you can find these in any order that you want. You could do the A1x if you wanted. So I'm trying to emphasize you do not need the previous term for these. You can do any order you want. I think this would come out to 1. A sub 2. Negative 2 squared and then plus 3. I think that comes out to 7 right there. Negative 2 to the 3rd power, I guess. Got the right or wrong. That'd be negative 8. Negative 8 plus 3 would be negative 5. So how do you find the sum? Here's the notation for it. You put s and then 4, the partial sum of the first 4 terms. And then it's just going to be 1 plus 7 plus negative 5 plus 19. That happens to come out to 22. That'll be it. Next one, this one's kind of a weird one right here. Find the partial sum here of the first, I guess this one's the first 4 terms again. So we're going to go find A1, A2, A3, A4. Okay, A1, so you do 4 over 10 to the first, which is the same thing as 4 over 10. That is 0.4. A sub 2, that'll be, let's see here, 10 squared down there in the denominator there. That'll be 4 over 100. That's actually going to be 0.04. Okay. A sub 3, do 4 over 1,000 eventually. And if you type that in the calculator, 0.004. So you can kind of see kind of a pattern going on here. This would be 4 over 10,000. That'd be, whoops, 0.0004 right there. So if you're going to do the sum of these here, it's actually kind of easy. 0.4 plus 0.04 right there would be 0.44. And then if you add on the 0.004 there, that'd be another 4. If you add the last one there, that'd be another 4 right there. There's your partial sum there, 0.4444 right there. And actually, we're going to kind of extend that idea here in just a second on the next page there, doing a different type of sum. So those are partial sums. Those are typically going to be finite type of sums. We're not going to add them up forever. You can just do the partial just like that there. Since an infinite series does not have a finite number of terms, you might assume that an infinite series has no sum. However, some infinite series do have sums. This happens when you have a converge. So for an infinite series to have a fixed sum, the infinite sequence associated with the series must converge to 0. I guess I don't need an S there. Converge to 0 right there. Okay, so if they kind of level off eventually, which is actually what's happening right here, this is leveling off. That's rounding to 0. You could actually technically do the infinite sum of that. On something like, I don't know, let's see here, like on this pattern here that we started with, since it's going up by 5 every time, you can't really find the infinite sum of this here because it keeps going up by 5, and you're going to start approaching infinity. So we'll do an infinite sum in just a second here. Before we do that here, we're going to talk about sigma notation. This is just basically a notation for the summation of things here. We use the Greek letter here. It's called sigma. And the symbol for it here kind of looks like this weird, kind of zigzagged looking E, I guess. And it is said to be expressed using sigma notation. Or summation notation. You're going to hear me say sigma notation a lot. So here's how it works. You're going to have an upper and lower bound here. This is your upper bound up here, this K. And then down here, this is going to be your lower bound. A lot of times your lower bound is going to be the one term, the A1 term, but you'll see here in a second that sometimes you can use different numbers. You can start your lower bound at the third term. So basically, like, yeah, this one down here, this is starting at the third term, going to the seventh term. You plug into your formula, like usually the right side will be some type of formula, whatever it is. That can literally be anything. So this is kind of a generic looking thing. And you just plug in and you add up all your terms. So this is just a notation for saying, hey, add all of your stuff up here. So that's all we need to do here is understand it. There are some buttons in the calculator where you can actually type in using sigma notation and it just spits out the sum to you right away. But a lot of these we'll do by hand. But there are some buttons in the calculator. You can look up how to use them if you want. So with this one here, this is saying here that we're going to start here A1, and then we're going to go all the way up to A5. That's your lower and upper bound. A1 is your lower bound, and then you have A2, A3, A4. And then eventually you get up to A5 and you stop. So this is kind of like, I guess, a partial sum here in a way. And all you got to do now is just go take your n values and plug it in to these explicit formulas right here. First one should come out to 1. 4 times 2 and then minus 3 right there. That should be 8 minus 3. And that'd be, what is that, 5? 4 times 3 and then minus 3. That'd be 12 minus 3. That'd be 9. And you can kind of see a pattern going on here. This would be 16 minus 3. This would be 13 there. Last one would be 17. And then all you got to do is just go do 1 plus 5 plus 9 plus 13 and then plus 17. And apparently that comes out to 45. So like I said, you can find the buttons in the calculator. I think it's under math and then you scroll down quite a bit of ways there. I think it's near the log buttons. Just use your calculator to punch that out. So. All right, let's try out a couple more here. I think we got a few more. So this next one here, we'll start out, instead of at the first term, we'll start at the A3 term. So you go A3, A4, A5, A6, and then A7 right there. So I guess another one with 5 terms. Okay. So A sub 3 right there would be 6 times 3, 18. 18 minus 3, you'll have to do that next, and then you'll divide that by 2 right there. Apparently that will come out to 15 over 2. That's about 7.5. Okay, the next one here would be 6 times 4 minus 3. And then all over 2. That'd be 24 minus 3. That'd be 21. And then 21 over 2 should come out to 10.5. And then you can kind of rinse and repeat here. It's going to be 6, I guess, times 5 minus 3. Divide by 2, that'll be 30 minus 3, that'd be 27. 27 over 2, that would come out to, what is that, like 13, I think, 13 and a half. And you can kind of see a pattern each time here you're adding 3. So once you start kind of catching on, you can kind of skip a few steps if you see a pattern. Okay, and then we'll just go and add up all of these together here. So your sum is going to be 67.5 when you do that. All right, let's finish up here. So this one here, what's interesting is your upper bound is infinity. So we're saying add an infinite number of these terms here. And it's actually similar to one on the previous page here. So if we start writing out some of our terms, I'm not going to write them all. I obviously can't because it'd go forever. But hopefully we can start catching on with this pattern here. This would be 7 over 10. That'd be 0.7. A sub 2 would be 7 over 10 squared. That'd be over 100 right there. That'd be 0.07. And then you can rinse and repeat here. That'd be 7 over 1,000. That'd be 0.007. Okay, and that'll keep on going forever. So basically, you keep adding, an extra 7 digit to the end of these here. So when you're doing the sum here, it's really just going to be 0.777, and it's just going to keep going. So, I mean, you can put your repeating line right there like that. Honestly, I'd probably just write it as 0.7 right there. 0.7 repeating, I guess I should say. So that'll be your answer there. There is a way to get the fraction for that. I forget, there is a process where you can go and do this here. I kind of forgot off the top of my head, but you could just try different numbers like 7. I think over 9 is going to get us the 7 repeating here. I'll get the infinite decimal on that right there. I think that last one we did, if you were to do the infinite sum with this here, like I think this one here would be 4 divided by 9 right there. So you can do the fraction if you want, but I would probably honestly leave it like this right here. And that would be good. So that would be it there. Now I did add in 2 extra examples here. I would encourage you to do the same here because there are some in the textbook here writing maybe a series in sigma notation. So instead of actually finding the sum, just writing it in the proper notation. So I took this first one here off of the first example that we looked at in the notes. So looks like here every single time here you are adding 5. So what we essentially need to do is just figure out some type of equation that's going to work out here for this here. So looks like we're adding 5. So I'm going to do 5n right there. And then you are starting at 2. And then I'm going to put my sigma notation, and then down at the bottom. Now, here's the thing. You don't start at 1 on this. You want to plug something in here eventually, and then get 2. And if you plug in 1, actually, if you do 5 times 1 and then plus 2, that actually will get you a 7. That'll get you your second term. So what I'm going to do here is I'm going to actually start it here at 0. If I plug in 0, that'll actually get you your first term there too. So this is kind of like your a sub 0 term. So this is a sub 1, a sub 2, 3, 4, and then this would be a sub 5 right there. And that's how you can go get your upper and lower bounds right there. All right. Notice how you went from 0 to 5, but there's 6 total terms. So you got to like actually include, the extra term, I guess. And then, so this would actually be your summation formula right there, or your sigma notation formula. And there's multiple ways you could do this here. If you wanted to start actually where you plug in 1 and get the 2, you have to do this little strategy here. This would be n equals 1 down there. And what we would do is replace n with n minus 1, kind of like this right here. And if you stick that 1 right there, that'd be 1 minus 1, that would be 0, and then 0 times 5 would be 5, or I'm sorry, 0, and then 0 plus 2 would get you 2. So that's what you would need to put right there if you want to start out at n equals 1. And then if this is a sub 1, and you go all the way up, the final term will be 6 right there. So this is another way to do it. I'd probably do the first one, honestly, if I were you, but the second way I have it is technically right. You could also simplify it down. Not sure if your teacher's going to require you to do it, so I'm going to go ahead and show you anyways. If you distribute 5 right here, that'd be 5n minus 5, and then simplify it from there. That'd be 5n minus, let's see, negative 5 plus 2 would be minus 3 right there. So this is the simplified form right there, but I'd probably leave it as the one there in red, and that'd probably keep you in good shape right there. So that is it. Grab it all. Okay, so that's that. This next one is actually kind of hard to write an equation for. This one here, I guess there's a few ways you can do this here. One way you can write an equation, well, here, let me just show you this here. So think about this here. 3 right there. The gap from 0 to 3, some people are going to say, hey, that's plus 3, plus 5, plus 7. And it's actually really kind of challenging to write an equation for, add 2 to the difference of these every single time. So here's one strategy that you can do here. I kind of like this here. I like to think of 3, and I'm going to write this here as 1 times 3. 8, I'm going to write that as 2 times 4. 15, I'm going to write as 3 times 5. And if you kind of start looking here, there's a pattern with these different products. 5 times 7, whoops. 0, I'm going to strategically write this as 0 times 2, following this pattern here. So notice here these front numbers are going up by 1 every time. Notice that the second number is 2 bigger than that every single time. So one way you can actually write your equation here is do n, and then whatever n is, the second number will be 2 bigger. Okay, so then you can put your summation notation here. And I guess the first thing you want to plug in, you want 0 to be your first number there. So you can start out at n is 0. And then that would go all the way up to 5 right there. And then you could leave it like that right there. So that's one way you could do it. Another way to think about this one is think about squares. Like sometimes these numbers here are related to perfect squares. If you look at them, well, you might be saying, well, no, not necessarily. But if you look here at 3, 3 is actually 1 less than a perfect square. 8 right here is 1 less than a perfect square, right? 9 minus 1 would get you 8. So there's kind of that right there. If you can recognize it, these are all perfect squares minus 1. So you could do this here where you say, okay, so we do n squared minus 1. Do your summation formula right there. Now you want to get 0 for the first number you plug in. So the only thing I can plug in right there and get 0 would be 1. So you'd have to start out there as that's your first term. So this would be first, second, third, fourth, fifth, and then sixth term right there. Okay, so that's kind of two different strategies to get your sigma notation there on those. And that'll be it here for today.